Um, this is just a short video on the calculations and statistics for lab reports because this is something we really need to have down. Um, so I've got some made up data right here. Um, and I want to talk about the data table, and then I want to talk about the statistics, and then the error. That's the goal here, as you can see it over the side here. Okay. So the first thing is look at your data table. The first thing is you should notice is that I've got separated the main 8 trials with the 5 repeated trials. Okay, these would be the ones where A was all like really close. We were trying to like do 1.5 A or something like that. Trying to do it every time, and we measured it, but we were trying to do the same value every time for it. And then we were trying to vary A a bunch up here. Okay. All right, and the two things we measured were A and B, and then we calculated C. Notice that Notice that 1A, trial 1A, is in both sets because it's both a part of the error analysis for that particular value of A we were using, and that it is also the representative of that particular value of A in the main data table where we're changing A. Okay, the second thing is notice that, or the next thing is notice is that these have units with them. They're labeled A, B, and C, which are just made up things, and I gave them made up units. None of these, well, they're not made up units, but the units don't match whatever I'm trying to calculate, but you should have units there. The final thing is look at the number of decimal places here. This is like a pet peeve of mine. Like this is the equation I used here, which is again is made up, has way too many decimal places. Like given that I'm using numbers that have like no decimal places or just a couple of like value or one value or a couple of them, 10.5 is like the longest one. This should have definitely no more than like 4 places. You can do that by highlighting it and just clicking this button right here, decrease decimal places, to something like reasonable. Like this is reasonable. Honestly, even shorter would be reasonable, like that would be reasonable. But like this is like reasonable. It's just like it's not a crazy, insane number of them. I don't want to see 10 decimal places. It's just silly. Okay. All right. So you got your data table, and yours might be more involved than this, obviously, but you should have the 2 different parts, and you should copy them in there. Remember that has to have everything that you measured and your final calculated value. And it can have more than that. But anyways, I measured A and B, and I calculated C. All right, that's what I did here. I'll make a note over here. Oh, no, it doesn't matter. All right, anyways, the next thing we have to talk about is the lab questions. There are basically 3 questions I'm going to ask you in a lab to try and show. The first is, does one thing affect another thing? Are they related? Is there, so any sort of thing where I'm doing like 2 variables, do they affect each other? All right, the answer to solve that is to create a graph of those 2 variables. All right, the easiest way to do that is to take these things and copy them into a different spot on the data table. You're not going to copy that into your final lab report, but you're just going to have it off to the side. So with this one, because these are just like values that I took, it's easy. I just highlight all. I want A to affect C, so I'm gonna have A. Then I need to copy C. Now watch what happens the first time I do this. I get zeros. Not good. Okay, there's a reason why that happens. Now I could just copy these numbers and like put them over there, but if you want to copy so that the numbers get copied from something you calculated instead of just the formula, when you paste, go to paste special, values only. And look at that, you get the extra numbers. If you just paste normal, it's going to paste the formula instead. It's going to adjust the formula and mess it up, and that's not what we want with the values. So now I've got the 2 things. All right, again, it is A affect C. I'm going to highlight it, insert a chart. Okay. Mine defaulted to scatter chart, which is good because I wanted it to. Scatter chart, but if you don't, it's the scatter chart. Use G as labels. Okay, sometimes you'll get this. This is bad. You don't want this. If that's what's happening, you want to use G as labels. Okay, so I've got it now. All right. Cool. All right. There's the title. There's the units. Please note that on the graph, I've got my value labeled, or the units on there. We'll talk about adjusting the scale in a bit, but first, that's not enough. To figure it out, I have to go to Series, add a trend line, show my r squared, and add the U's equation. All right, my r squared here is 0.246, which is good. That's low. Well, probably good. I wanted to know, does A affect C? This means no. A does not affect C. So r squared is less than 2 or less than 0.5. So the answer is no. Now, obviously, if you wanted it to affect one with one to affect the other, that would be bad. If you don't want it, that would be good. Doesn't matter. Okay. All right. So we got our graph. Get out of this. We'll make. Actually, we'll just do this right now. We'll do the parts in part 3 here. This actual graph is not bad at this point. I've got my axes labeled with units. My horizontal scale is good. You could, if you really wanted to, change this value to be like 0.5 to 0.05 to 0.1 or something like that, or to 0.15. Okay, just like, you know, have it more centered. You could even do like no, none of that matters. Don't ignore that. Ignore that. Mess with that. So you could also do like you could even go to 0.8, 0.08, yeah, to 0.14. That might be a good one, right? Okay, so just like something like that to get at that. But honestly, it wasn't that bad to begin with. If you ended up with 0 to point or 1.5, that's fine. It really doesn't matter very much in this particular case. That's fine. What I don't want is I don't want it to be like, I don't want like negative 0.2 all the way down there. Like this would be, if it somehow defaults to, if it somehow defaulted to negative 0.1 or something like that, that's a really bad graph. Like, what are we? Why are we showing any of this negative area? It doesn't make any sense to have it even on the graph. Okay, so you want, again, I'll go 0.05 on this right there. That's about what I would want, ideally. But there's, you know, there's a lot of wiggle room there, but just like don't have lots and lots of space that, like, you know, like I don't want you to not use like 95% of the y-axis. Like, we're using everything from here to like here. That's like a quarter to a third of the whole axis. Okay, use at least that much. All right, let's get this out of the way. The title, honestly, you can have the title or not. I don't care. As long as your axes are labeled, you can get rid of the title or you can have a title. Doesn't make any difference to me. All right, the second question that you might be asked: is C equal to 0.1? Okay, that would mean this is an expected value, of 0.1. Is C equal to 0.1? Well, to do that, you need to calculate do a few things. The first is you need to calculate the average. So I'm going to calculate the average. Type equals average, open parentheses, highlight it. There we go. Huh. That's really interesting that it just happened to be exactly the same in my last trial. Totally random. Okay, the second thing you need, so first of all, the average is not exactly 0.1. That's not great, but it's not the end of the world. Second thing I need to do is I need to calculate the standard deviation. So equals STDEV, highlight, close. Okay, there's my standard deviation. We can reduce the number of decimal places there as well. All right, final thing, 4B, is C equal to 10? I need a z-score. Okay, a z-score is equal to the expected value, 0.1, minus, undo, what did I just do? I did not mean to do that. There we go. Okay. All right. Z-score, which is equal to the expected value, 0.1, minus the average, there we go, divided by the standard deviation, negative 1.33. The negative part doesn't matter at all. Is C equal to 0.10? My z-score is equal to 1.33, which is less than 2, so I mean, is it 0.1? We don't know for sure, but our data is consistent with C equaling 0.1. Okay? All right, that's one thing. Now, you'd never have both B and C. The other question you might ask is, what is C? Okay? Well, if you're asking what is C, then you wouldn't have a z-score. Get rid of it. All right, you wouldn't calculate. There's not an expected value. What you would do is you would create an interval for this. Now, your best guess for C, is 0.1117. Of course it is. That's the average. It's your best guess. Why not? But we don't know if that's true. Okay, so instead we want to create a little bit of wiggle room for ourselves. And the way you create a little bit of wiggle room is by creating a confidence interval. And you're going to have an upper bound and a lower bound. The upper bound is going to be equal to the average, okay, plus 2 times your standard deviation. And the lower bound, was that autofilling it? Is that going to show the formula? Oh, hey, that's, oh, no, it's not. Okay, ignore that. That was a bad autofill. The lower bound is going to be equal to the average minus 2 times the standard deviation. Okay? So the answer to what is C is almost surely between 0.942 and 0.1292. Oh, 0.0942. Okay? That's the answer to that question. What is C? Okay, and again, you only have B or C. You won't have both. All right, but this is the answer for it. All right, we already did label the axis on there and adjust the scale. We already did that, so let's talk about random error. Okay, the first thing is reasonable error. This is what you're doing with your repeated trials. All right, A and B. These are the measurements we did with our repeated trials. Okay, notice I did not have to calculate C for the repeated trials. Don't need to. Doesn't mean anything. What I need is I need to calculate the reasonable error from my measurements. So I only need my measurements for the repeated trials. So the way I do that is the reasonable error is the biggest value, 1.6. I need to do one more thing. I need to average these. Before I do that, average this the average, and I need to equal average. Okay, so sorry, I got to average first. All right, now I need to take the reasonable error is equal to the biggest 1.6 in parentheses 1.6 minus 1.45 divided by the average. So about 9.8%. I do that with both of the things I measured. So I also measured B. B is equal to the biggest, which in this case was 11, okay, minus the smallest, 10.2, divided by the average. Okay, now which of these is bigger? This one. So this becomes my error, my reasonable error. Okay, it's almost 10%, is like the maximum reasonable error I should expect to get from my measurements. All right, now I'm going to end up comparing that to the coefficient of variance. Okay, the coefficient of variance is easy. The coefficient of variance is, you've already done this, is standard deviation divided by average. Okay, and it's about 0.078, 7.8%, which is less than the reasonable error. I'm saying maximum reasonable error, really. Okay, so that's it. Those are all the statistics you need. Okay, you're still going to have to obviously interpret them in the lab, but there's no good reason not to have the numbers actually work out. Okay, now remember, is it a z-score? Okay, oh, reasonable error here, we can say it is 0.098. We'll go up a percent, or actually, so this is 9.817%, and the coefficient of variance was 7.845%. Keep hitting, this keyboard is not doing nice things for me. Percent, there we go. Okay, so those are my coefficient of variance and reasonable error. And you can leave it in decimal form. I did it in percent form here, but it doesn't matter to me. Those are the things the statistics you need to have in any lab report in this class. Okay, you need to have the error, and you need to have the things that will answer these questions. Whether it's if we're asking if something affects something, you need to have the r-squared, which means you need to have a graph. If you're asking is a value something, you need to have a z-score. If I'm asking you what is the value for something, you need to have this upper and lower bound. Oftentimes it's called the confidence interval. You don't really need to mention that, but it's like the upper and lower bound. And you would say, well, the average is 0.1117, and the likely value of it is somewhere in this range. All right, that's it. Make sure all your numbers are right.